array I plus plus, यही होगा ना, ठीक है. Sum plus is equal to, and you initialize sum to 0 here. Sum plus is equal to array I plus plus. So first it will access the first element, then it will point to next. So actually, if you look at the assembly code, the assembly A0. So how we can initialize A0? So अगर assembly की बात करें तो assembly में हम इस तरह नहीं कर सकते. Move A0 hash which addressing mode? Immediate. Which address? 0x $0x 2000. So what we do? Which addressing mode is this? Register addressing mode. Remember?
Yes, sir.
Because there is R, now there is A. Now we just change the notation of it. So it means 0x 2000. It will point to the first location. And then when we are doing some operations, so actually you can then access reset indirect with post increment. When you do this post increment, then you have loop counter. You initialize that counter to some register R0, and then you decrement that counter. So if you have 100 elements, so the loop counter is initialized in some register. Let's assume R0. Move R0 is equal to hash 100. And when we access the first element, then we perform an add operation. And we reset indirect with post increment, then we decrement the loop counter, then we compare with 0. When it's 0, we exit the loop. When it's not 0, jump back to the loop. And we will do this maybe in our next lectures. Okay. So now this is, so that's the actually if you look at this register indirect addressing mode, it is actually used to access some elements of an array typically, and register indirect with post increment is used to access the elements of the array in a top to bottom order. Register indirect with pre-decrement is used to access the elements of an array bottom to top order. What about register indirect with displacement?
We can jump multiple positions in this.
No, register indirect not jump position. Now, it's a very good question. Anybody can give me a hint, he may get some bonus marks. तो देखिए यहाँ पे ना सोचना बहुत जरूरी है. जब तक आप सोचेंगे नहीं ना, आपने अपने जो ब्रेन को है इसको स्टिमुलेट करना है, इसको स्पार्क देनी है. ठीक है, आप सारे जो C++ के जितने भी कॉन्सेप्ट्स थे कि आप इसको इस साथ लिंक करने की कोशिश करें. जब लिंक करने की कोशिश करेंगे ना, तो एक्चुअली यू लर्न हार्ड. ठीक है, अब हम लोग देखेंगे कि now let's assume if you have an array, now in this example we have an array E0. Who is pointing to E0? Who is pointing to E0 element 0? A0. It means E0 is pointed out by an address register. Pointed out by address register. Now this address register contains the base element of the array. The base element means the first element of the array. Now if you want to access E15, we don't want to access E1, E2, E2, only want to access E15, the 15th element or 16th element of the array. How can we access it?
We need an offset.
We need an offset. Very good. We need an offset. Okay, if you use register indirect with pre-decrement or post-increment, so the cost will be higher or less? High. Okay, because you need a loop counter, then you need to increment, you need more number of instructions. So without using a loop counter and accessing an element of an array, so there is a formula. So what is the address of the nth element of array? So the address of the nth element of array is equal to, now let's say you have an array, the base address plus n minus 1 multiplied by size. What is the size here? 4 bytes. Actually, if you say, because we have a jump of 4 for long, very long, maybe we need 8 bytes. So size may vary, but in this example we have. So now let's assume if we say E0 0x 200C E3 0x200010 E4. Am I right? 0x2014 E5. So now, what is the address? Okay, now what address of the 0, 1, 2, 3, 4, 5. So this is the first element. This is the second, third, fourth, fifth, and sixth. So what is the address? The address of the sixth element of array. Sixth element of array. The address of the sixth element. What is the sixth element? Actually E5, because the indexing starts from E0. Okay. So it is E5. What is base address?
E0.
E0. 0x2000.
Yes.
What is n? Sixth element. 5, 6 minus 1 multiplied by 4. So if we say 0x2000 plus 5 multiplied by 4, 20. 20. But if we convert it into decimal, 20 in hexadecimal, 20 in hexadecimal, 16. 16 ones are 1 4. $14. If you add this, what is the new address?
201014.
And if it is the first element, it's very simple. The first element, 1 minus 1, 0, and actually the base.
Yes.
Okay, so actually, and if you look at this, this is called as the offset. So actually, if you look at this, this is the offset. Okay, now the offset can either be positive or offset can be negative. So offset can be positive when we want to move
From 0th element to
from top to bottom. The offset will be positive, and from bottom to top it will be negative. So the offset may be positive or negative. So how do we do this? So actually, if you do this, so actually this is research indirect with displacement address. So what is the mechanism? So can we can write it like this. So now if we say and actually if you look at this plus size, okay. Move R3 dollar. Okay, now what's the offset here? 14 $14 and 80. So this is the syntax. So you have registered indirect. With post increment you have plus here. With pre-decrement you have minus here. And with displacement, what is this 14?
It's an offset.
Offset. So how it will look like? The register indirect with displacement will look like this. AK. What is K? K is an address register. AK is an address register, and it is a offset. So what is the effective address? Okay. Now in this case, the base address does not change. The base address is still pointing to that location, but only the effective address is changed. Sorry, the effective, you need to find an effective address. So what is an effective address? So what will happen? Okay, move R3. Let's assume that the old contents of R3. Let's assume that the old contents of R3 is E5. Now E5. This content is 0x11223344, and the old contents of R3 is 000000000. These are old contents. So actually, what is destination? Register. So the contents of R3 will be updated with the update. Wait, the contents of the memory. The contents of the memory at A0 plus 14. This is the So what is the effective address? The effective address is 2014. This location will be accessed, and which data will be moved here? G.
The contents are 2001.
2014. The contents is 0x112233 and 4. In this scenario, in research indirect with displacement, A0 does not change. It is 0. that it will remain unchanged. Okay, but it is just used to, it will still point to the base address. It will still point to the base address. But in recent indirect with pre-decrement, it will change. It will recent indirect with post increment, it will change. Post increment, it will change. Why? Okay, in pre-decrement first it's changed, then accessed. In post increment, first access the element, then increment. अब देखिए, there is a little bit difference. अब ये समझे या नहीं समझे? Okay, in recent indirect, the address register is not changed. With simple address register indirect, the address register is not changed, and actually it is an effective address. With recent indirect with pre-decrement, first the address register is changed, the memory location is accessed. In recent indirect with post increment,
First is access.
first the memory location is accessed, then the address register is changed. And recent indirect with displacement, the address register does not change. That address register is added, the contents of the address register is added with the contents of what?
Effective. It contains a certain offset.
It is added with the offset value. It will find an effective address. That memory location will be accessed, but the address register is not changed. It will remain unchanged. A0 will still be 0 to 0 0 0. Okay. So these are all example of address mode. These are some notes. These are available on the Google Drive link. अच्छा आपने now we will study stack addressing mode. Stack is actually a data structure which is called as LIFO or FILO. LIFO. What is LIFO stand for? Last in, first out, or FILO. First, last out data structure, which is typically governed by two types of operation. One is called as push operation, one is called as pop operation. Okay, stack, and actually if you look at the stack, so actually stack has only one end. Stack has only one end, and this end either you can perform a push operation or a pop operation. So now I will explain stack with an example. Stack with an example. So now let's assume this stack is typically pointed out by some address register that will be called as a top. Top is a register, and it is typically pointing to the bottom address. It is not pointing to any address. It is not pointing to any address. It is just like a dangling address register, a dangling pointer. Okay, it's not pointing to any address. But when you perform in any operation push R0, so it means that now the stack is pointed out by top, so actually the top will be updated and it will move to the bottom location, and the contents of R0 will be moved to the stack. So now let's assume we have push R0, so let's assume we have some register R0, R1, R2, R3, R4, R5. These are some registers. And let's assume these values are line 2, and for the sake of simplicity I am taking some small values. For the sake of simplicity, 2, 1, 3, 2, 9, 6, 3, 1, 3, 6, 4, 8. Okay, so now push R0, so what we are doing, we are moving the contents of R0 to the stack, so it means, and now top is pointing to this line 2. And when we again push R3, so now a next element will be added to the stack, and which value will be moved to the stack? 96, and then top value will be updated. But and then we have another push R1, then element. You cannot access 92. To access 92, you need two pops. 93 pops. Not one pop. First you have to remove this. Like it's just like a stack of utensils. It's a container. It's a box of container. This is container, and you put one utensil. Then you put second utensil. Then you put third utensil. Can you access the bottom access?
No.
If you want to access the bottom one, you have to
Remove the
remove the first
first.
two tops. That's it. So then top is now pointing to this location, and then it is. Now there is another operation which is called as pop. Pop R5. So the first element will be moved from the stack,
5.
and which value will be removed? R5.
21.
So the contents of the top will be moved to, so the new contents will be 21. And now where the top will point?
96.
Now if you look at the stack data structure, so actually the data will still be there. The data is still there. Okay, now if you are maintaining this stack, so we are moving from the bottom to top or top to bottom? Bottom to top. So actually, which addressing mode should be used?
Pre-decrement.
Reset indirect pre-decrement. समझ आई बात?
Yes, sir.
Reset indirect. Okay, now when we pop R5, the contents on the top of the stack will be moved to R5, but this content will still be there. It will not be overwritten. When it will be overwritten?
जब
Until
दोबारा
a new
वो-
value is assigned. So if you say push R4, so again top will again point here, and the new contents is what?
36.
36.
So actually you have to understand the stack from you have to understand the stack from the perspective. You have to understand the stack from the perspective of addressing mode. So and actually it is the address is moving from bottom to top. When stack is used, now this is another question. When stack is used,
इंटरप्ट आ जाए
interrupt आ जाए. Interrupt. We'll study this in our later lectures. Okay, अगर मैं अभी चेक कर दूँ तो हो सकता है आपको. Okay, now I have one question from you. If you want to swap the contents of the content of two registers, how we can achieve this using stack?
You do push and do pop operations.
Yes, how? In which sequence? Let's assume we want to swap the contents. Now let's assume we have R0, R1. Its content is 9, 2, its content is 3, 6. We want to swap these values. 92 should be moved here, 36 should be moved here. How we can do it?
36 को पुश कर लेते हैं सर
R1 and R0 and R1 first.
दोनों first time.
पहले दो पुश होंगे सर.
Okay, now stack. Can we do it like this? At time t1, then we have time t2, then we have time t3, now we have time t4. Anybody wants to come on the board and solve this problem? If we say push R0, stack
92.
92 आ जाएगा
92. Okay, so the contents of at this point push R0. So the content of the stack is like this. This value will be 92, this will be 36. Then second instruction push R1 92
36.
36. 92 will be here, 36 will be here. Now what should we do?
Pop 36.
Pop R0 R1 because we want to move 36 to R0.
Pop R0.
Pop R0. Pop R0. 92. The top element will be. So what value will be in R0?
90.
36. 36. And R1?
36.
And then
Pop R1.
Pop R1.
R1. 92 will be moved. 36 and. So now we can also have another. This is one method. Can we a little bit optimize it?
Move instruction use.
You can also use move. Yes. अगर हम करें push R3, this is one method. अगर हम करें push R3, push R3, stack पे आ गया R3. What will be the contents of stack? Sorry, push, not R3. Push R0. What is the content of stack?
92.
92. Okay, now what will be the contents of R0 and what will be the contents of R0 is here 92. What is the contents of R1?
36.
Which value is pushed?
92.
92. When 92 is, so can we do it like this? Move R0 R1.
R1. Yes, sir.
Move R0 R1. So so what will be the contents of
36.
36? Now what are 36? Then
Pull use कर ले sir.
pop.
Yes, sir.
Pop what?
Pop R1.
Pop R1. What's the advantage if you compare these two? What's the advantage? What's the disadvantage?
Less number of instructions.
The number of instructions are reduced. So actually, if you are writing a code in C, so actually how many instructions will be realized? How many instructions will be, if we assume that the size of each instruction is fixed, so if you reduce the instruction count, so you reduce the code size. You reduce the code size. If you reduce the code size, you have an advantage. You have smaller application footprint. When you have smaller application footprint, it requires less memory. When it requires less memory, so maybe it's easy to execute faster. So these are the scenarios that you study in this, like code. Okay. So these are a lot of details, push and paste. When you initialize a stack, let's assume also when you have some memory. Okay, so this memory, so actually in memory is divided into different regions. Memory can store instructions. पहले क्लास में बताया था ना?
जी sir.
It can store data. It can also stack. So some space is reserved for the stack. Maybe it's done by the operating system level. So it's done by the operating system level. So actually, now it's very important. It's very important that if you are maintaining a stack in memory, so you should avoid an underflow or overflow. You should avoid an underflow or what is an underflow?
When the stack is empty.
When the stack is empty, you want to read the data. So actually, you cannot use a pop operation. You have to push some data and then you have to read the data. So it is an underflow. When the stack is empty and you want to pop some operation, the stack is not initialized. It does not end and you are popping, so it is an underflow. What is overflow?
When the stack is full.
When the stack is full, let's assume your operating system has reserved some portion for the stack. Let's assume that portion is 4 kilobyte or 8 kilobyte. Let's assume. And if it is pushing something and it falls within the memory region of other application, so it is an overflow. maybe did you get some kind of these kind of errors in your C++ stack, overflow stack, and all? This. Okay, so basically, if you want to have a stack, so you should check that whether the stack is full or empty, and these are some detail in the notes. Please go through these notes because these are undergraduate course, so actually I'm not going into much detail in this here. Okay. बहुत स्लो जा रहे हैं. जी अब अगर आगे जाते हैं हम कहते हैं कि now we have some status register within the microprocessor. Microprocessor has some dedicated status register. We call it as SR. SR. It is a special purpose register and it has some flags N, Z, C and V. What does N stand for?
Negative.
Negative. Z stand for?
0.
0. C stand for?
Carry.
Carry. V stand for? Overflow. So these are different type of flags. Negative. So the N flag will be 1 when the result of any operation is negative, and it is 0 when the result of operation is positive. What about Z? Z will be 1 when the result is
0.
0 and 0 result is non-zero. Non-zero, it may be positive or it may be negative, but it's non-zero. Carry. Carry.
One carry operations.
When there is a, when you add two bits to data, let's assume we want to perform any operation. So let's assume we have used this. We have performed an addition operation. So we have an addition operation, and let's assume that the size of the data is 16 bits. The size of the data is 16 bits. We have two operands A and B. So A and B, so it will start from A0, A1, A2 up to so on and A50. Then B0, B1, B2 up to B15. When you add these 10 and there is a carry generated from here, it is called as C is equal to 1. So the carry will be 1. The carry
Overflow
will
नहीं
be
होगा सर.
what?
ये overflow नहीं होगा.
No, it's carry. It's carry.
ठीक है सर.
Okay, now I'll explain it. You have asked the question. It's a very undergraduate का है digital logic design. वो तो उससे अभी पहले कर दूँगा. Let's assume that the size of the data is n bit. When you add two numbers, so let's assume if we have C is equal to A plus B, and this A is n bit, this B is n bit. If you add two n bit number, the result is n plus 1 bits. Agreed or not? If you have this ripple carry adder, so you have some sum and C out. So sum is actually n bit and C out is 1, and it is actually that C out. And it is actually that C out. So now if you say like we have 3-bit data, so let's say if you want to add 101 and 110, so the result is 1110 and is 1. So the carry is generated. This card is a carry. Carry is generated. Okay. Overflow is different. Overflow is different. I will explain this why it is different. Why it is different. Now, overflow is carry generated when you add two positive numbers. When you add two positive numbers and the result is negative, then error flow is generated. If you add two positive number, what should be the result? Positive or negative?
Positive.
It should be positive. But if the result is negative,
It's an out.
then error is error. Now I will explain this with an example. Now I will refresh your concepts of digital logic design now. And I will explain this with a very simple example. Let's assume we have a 3-bit data. For the sake of simplicity, we assume we have 3-bit data. We have this bit data B0, B1 and B. So how many possible combinations are there? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And let's assume now there are two representations of the data. Either this data can be signed data or unsigned data.
Yes, sir.
If it is unsigned data, so it ranges from 0 to 7.
ठीक है sir.
But the complexity arises when we assume that this data is signed data.
Signed data.
So it is actually 2 to the power 0. It is 2 to the power 1 and it is minus 2 to the power 2. Its weight is 0, sorry, 1. Its weight is 2, its weight is minus
4.
So actually this data is equal to 0, 1, 2, 3. 1 double 0, minus 4, minus 3, minus 2, minus 1.